Shariat. I'm a graduate student at Caltech working with Kareem Al-Badri. And today, I'll not only tell you about triples and low mass X-ray binaries, which was the original talk, but I just want to take you through a journey of triples and their role in the stellar population. This is in collaboration with Smadar Naos and also Kyle Rocha and Vicky Caligara and many other people that are not here today. So first on LMXBs to acquaint us all on a typical LMXB, to get order of magnitude numbers in mind, you think of like a 10 solar mass black hole accreting from a 1 solar mass donor at a separation of say 0.1 AU, and the typical age is a few gigayears. And so the natural question is, you have a black hole right next to a sun-like star today. How did it form? And so a priori, we think, let's go to binary evolution, and that black hole was a 2030 solar mass primary star in an intermediate orbit. It evolved, underwent nuclear evolution, expanded, began mass transfer with its companion. That mass transfer is expected to be dynamically unstable given the mass ratios, leading to a common envelope event. And if you completely eject the envelope and you're right next to the helium donor, that helium core will collapse. You get a black hole next to a main sequence star, which will lose angular momentum and become a black hole low mass X-ray binary. And so that's the canonical binary evolution picture. And if we revisit the timeline that is proposed here, we see that there's a huge uncertainty, the main one being surviving common envelope. It's not at all clear that a solar type star could survive common envelope and has enough orbital energy to eject the envelope. The second uncertainty is during core collapse, whether that event could keep the binary orbit bound. And so we want to revisit the question and wonder if this is the correct picture. And so we've seen this plot before, but this is the triple fraction as a function of primary mass. And as Smadar said before, the natural place to start for these O-type stars, which are your black hole progenitors, is with a triple star system. Now, whether you stay as a triple forever is unclear, but let's at least start there. So let's re-ask the question of how do BH-LMXBs form, but this time start with a natural approach, which is by considering a third star there. In this scenario, so we know that all triples are hierarchical in nature, at least most of the ones we observed. We saw yesterday that's true for massive triples. For low mass triples, we see that as well. And in this, you get the aforementioned Kozai-Lidov oscillations, whereby the inner binary fluctuates in eccentricity and inclination. And how does this help you? Well, you can go back to your 30 solar mass plus 1 solar mass binary, and this time widen it so that it never interacts. So let's say 50 or 100 AU away initially, and you have a third star just chilling. And so this allows the primary star to evolve into a black hole without ever transferring mass to its companion. And so now you're left with this pretty wide inner orbit that's 100 AU that would otherwise do nothing in the galactic field and be difficult to even detect with Gaia. And you have a tertiary, say 5,000 AU away. But now this is prime time for Kozai to enter the room. So this, on secular timescales, the inner binary, whether you like it or not, will experience gravity. And this gravity will lead to eccentricity oscillations through Kozai. And these eccentricity oscillations can be so strong that the inner binary's eccentricity becomes extreme, whereas such that the periastron becomes small enough such that tides can efficiently dissipate orbital energy from your orbit, shrinking and circularizing you into a low mass X-ray binary, notably without ever experiencing a common envelope phase. No faith needed for this formation channel, just gravity and basic stellar evolution. So that was all just a proposed channel, but it turns out that one of the most prototypical LMXBs that was mentioned earlier is actually in a triple. And I say one of the closest and one of the prototypical LMXBs because had this been a bit farther, it would be unresolved. You wouldn't see that it has a common proper motion companion. And had it been a bit fainter, you also wouldn't see it. So this is a little bit interesting because it makes you think, did we get super lucky or are tertiaries just common around LMXBs? Future work is needed there. But I want to say that that was just one proposed channel and motivated by the fact that there is an observed system. What I'm interested in doing is saying, in a landscape of both binaries and triples, what is the role of triples? So what I did is I ran a triple population synthesis. I initialized all types of triples with semi-major axes and masses using our state-of-the-art simulations that include gravity. They include stellar evolution for each star using MESA grids As far as I'm aware, this is the first time this was implemented in a triple code self-consistently. We have short-range forces like tides and GR, and we also include natal kicks. So that's 50,000 systems, and we evolve them for 10 gig years. And what are the results? Well, I'll summarize them on this plot, where the x-axis is the semi-major axis of the inner orbit compared to its eccentricity, and then compared to the semi-major axis of the outer orbit. So if we first looked at the systems where the inner binary remained detached, so no LMXPs here, you just have a detached black hole and main sequence star in the inner binary, you see that they span all throughout this parameter space, and the color just tells you what is the stellar type of the secondary here. It turns out that 14% of these detached systems did not remain detached in triples. 14% actually led to accretion and formed an LMXP. And those you can see here. So they have small inner semi-major axes, they're circularized, and if you look, the tertiary likes to be between 5 and 10,000 AU. So why is that? It's because these all formed through the no common envelope scenario. So the inner binary had to be 50 to 100 AU initially, meaning the tertiary for a stable orbit had to be a factor of 10 farther than that, which is 5,000 to 10,000 AU. Factor of 10, 5 to 100. So if we look at V404 Cygni, we see, interestingly enough, its tertiary is right where we would have expected it to be had it never experienced common envelope. Interesting. It's also a little bit evolved, which you see we have a little bit of preference for given the tides. So I haven't even brought up black hole natal kicks. Those simulations assume no natal kicks. So if you do assume natal kicks, you see that you're on a few kilometers a second trajectory if you are the tertiary. And so any natal kick would presumably unbind you. So we can set extreme constraints on natal kicks. So in our simulations, we run another batch assuming some fallback kicks, and we find no LMXPs, and actually only 5 of the 200 systems evolved, and these were all the ones that got small kicks, less than about 10 kilometers per second. So it turns out, so we have these, you can form with, without natal kicks, with and without common envelope. So we run a full population with binaries, with triples, to see how much would this actually contribute. So we have an isolated binary channel with and without kicks, and we have a triple-only channel with and without kicks. And it turns out that if you crunch the numbers, the fraction of low-mass X-ray binaries shown on the y-axis is super high in triples, even with kicks, compared to just the isolated binaries. This is because you get higher eccentricities and more mass transfer events in triples. And if you don't believe in common envelope and you test all these populations, you find that triples is an extremely efficient way to form low-mass X-ray binaries. So let me just conclude by wrap this up by saying triples form them more efficiently without a common envelope compared to isolated binaries. In a landscape of binaries and triples, we predict that 80+% form this way. And V404 itself, we predict, formed this way, and that it got virtually no natal kick, less than a few kilometers per second. Okay, that was the first third of my talk, and I'm going to speed through the rest. But I'll just say LMXPs are rare, and I was interested in learning more about the role of triples on accreting binary populations. So there's this other class of system known as CVs, and that looks like your normal LMXP. You just swap out the black hole for a white dwarf. And these are much more common by a factor of many. And the good thing about being so common is that you can actually go out and observe them. So we go to Gaia, and we observe some 50 CVs in triples, and this has never been done, that people have systematically looked for CVs. And the fact that 50 are in triples is really cool. And so we also run a whole batch of simulations to say what are our predictions for the observational signatures of CVs formed in triples. Here are your favorite CVs. Here they are in the HR diagram. And we find that 20% form through the normal way. They would have formed if they were in binary, so triples don't do anything. 60% would have never become CVs in isolated binaries, but because of the eccentricity dynamics in triples, they were forced to transfer mass and eventually became CVs. And CVs, which we call post-common envelope binaries, turns out that some fraction of them never experienced the common envelope because they're in triples and formed through the aforementioned channel. And so it turns out that triples are crucial for the CV population, and we predict that 40% of triples of CVs in the galactic field form through one of these triple channels. That is greater than 0. So in the last third of my talk, I want to quickly talk about where we are and how we're moving forward. And I'm interested in understanding the demographics of the triple population. And so this is what we have in mind when we do binary population synthesis. This is what I have in mind when I look at the galactic field. And so in this work, it was purely observational. We went to Gaia, and we got a homogeneous sample of 10K triples. And the beautiful thing is that it's easy to completeness correct because our selection function is well characterized. And I won't tell the results, we can talk about it later, but we constrained the intrinsic masses and mass ratios of the triple population, the periods, the eccentricities, the mutual inclinations, and the triple fraction. And we can talk about that more because I have -2 minutes left, but there's a public code where you can easily sample a triple population, and if you'd like, a full stellar population with singles, binaries, and triples that match your observational constraints on the stellar population. You can use it for rates, population synthesis, initial conditions, whatever you want. Okay, I'm getting kicked out, so that's all I'll talk about, and I'll leave the conclusions up here and take any questions. Thank you.
Okay, to Carl.
Hi, Carl Rodriguez, UNC. So great talk. I'll start with a very provocative question. Let's say that I don't like the common envelope, just on vibes entirely. Could I do away with it entirely and replace it with triples? Is there a way I could completely eliminate the production of short period binaries by common envelope just with triples?
All short period binaries or just low mass X-ray binaries?
Let's start with the latter and move to the former.
Okay. All accreting binaries, no. So CVs can form post-common envelope. I mean, there's a lot of evidence that a lot of them are just isolated. And so that I'm okay with. There's no extreme faith arguments. When it comes to LMXBs, we do a calculation that if you just want to form through the no common envelope channel, depends significantly on your assumption of black hole natal kicks. But if you assume something, let's say you assume no kicks, then you get as many LMXBs as you want because it was so efficient. I mean, 14% of detached black hole main sequence binaries, if they're in a triple, experience strong EKL effects and become LMXBs. So there, I think it's okay. But if it turns out that that you get strong kicks super frequent, and this is an outlier, then I think you need some other arguments of forming low mass X-ray binaries.
I will say we see luminous red nova, so we know common envelope exists. But...
Yeah. I believe in common envelope.
Also, we have neutron star LMXPs, and you can't avoid the kicks there.
Yeah, maybe Jakob Stegman is also a great person to talk to there. Yeah, question.
Hi, Shariat. This is Jessica Liu, UC Berkeley. I have a question for you. Great talk, by the way. On the observing side for the Gaia triples, did you look to see that these aren't part of sort of pseudo small star clusters or streams or anything like that?
Very good question. The answer is yes. So I do a search where I look for common proper motion companions, and the first major contaminant are open clusters where you find that one star has 30 companions. So it's not just a triple, it's a 30 tuple. And so I remove everything with like 5 or more common proper motion companions. Anything with more than 3 goes to the appendix, and I focus on those with 3 stars total.
Hi, Cheyanne. Super cool work. I have a question. When you infer like low mass X-ray binaries or CVs with coming from triple interactions rather than isolated binary evolution, and they're highly eccentric, do you expect them to be last different time amounts, like the duration of these X-ray binaries and these CVs probably are shorter because it's only on the paracenter? Have you thought about that? Do you have any predictions for the time duration?
Yeah, so for the CVs, there's a clear prediction, and that is that in this formation channel, at mass transfer, you prefer slightly larger donor masses, the secondaries. So that's because the radius is slightly larger, and then a larger radius gives you a higher probability of tidal capture. And so we predict that their initial periods are a little bit longer, and if they have higher mass secondaries, then they would live for a shorter amount of time, because if you're an M dwarf, you'd live forever as a CV, and if you're a 1 solar mass star, you'll eventually evolve. And so it's also a prediction on the fraction of CVs versus like evolved versions of CVs, AMCVNs, et cetera. For the low mass X-ray binaries, the typical time scale is gigayears. They're observed for gigayears, and they can survive longer because you get red giant donors as well. So I don't know if there's a clear prediction given our age estimates of LMXBs today, but there is a prediction on the time distribution of how old these systems could be and how long they last as accreting binaries. We can talk more after as well.
We can probably do a very short question. Who has the shortest matcha? Okay. No?
Give you the mic after.
Neve, you have short? No. You're short? Okay.
Can you calculate the rate of luminous red novae, like Carl was saying, for all the mergers that you will drive through Kozai during
Yes,
the stellar evolution?
So it depends on what mass ratios you think those luminous rovae. Do you think they're 30-to-1 mass ratio, or do they think they're just your normal AGB star engulfing a M dwarf? Yeah, I agree. That would be a good next step.
Let's thank Cheyanne again.